Well, let's get started. Good morning or good afternoon if you're in Europe. Today's lecture, it's on a new topic. Most of it will be on a new topic, on connectivity. Not introduction to continuity, introduction to connectivity. And but first, I want to finish a little bit what we discussed last week about product spaces and continuities to give you a very easy and quick way of proving that, say, sums of functions are continuous, products of functions are continuous. So these are a little disjoint, and they will form two different topics for today's class. Of course, both involve continuity, so in that way they are related. Okay, so continuity of product spaces and introduction to connectivity. And both of these have just to give you a little heads up of what we'll do, we'll start kind of slow, review a little bit what we said on Friday, and prove a few statements there. Then we'll state a theorem about continuity in product spaces, and then we'll give an application to that to showing that various things are continuous. Then we'll switch gears and start talking about a new notion, connectivity, motivated through examples. Give the formal definition that's a bit abstract, and that's why we're motivated. And then we at least state the theorem that 0, 1 is connected. If we have time, we will prove those claims. Okay, so let's review a little bit what was done last time. So a bit, or not on Friday, I mean on Wednesday before the exam. So we had a product space consisting of pairs where x is in x and y is in y. And we have a distance function on it. There are different choices of this distance function, but the standard one that most of the people use is you take the distance of 2 points, so with components px, py, and qx, qy. The distances of the distance in the x components. And I'll often denote the components by a subscript. That way, we don't have to always introduce a new notation for the components. So distance in the x component squared plus distance in the y component squared. Okay, so now something that has come up in a lot of discussions, there are some standard estimates that I decided to collect in this lemma that are useful in proving things about these inequalities, and we'll see how they are useful in these basic things. So the first thing is that if you have 2 points, someone should draw a picture of this. So we have the y factor, we have the x factor, we have our 2 pair of points, px, py, and qx, qy. The distance, sort of the length of the hypotenuse. I mean, if these were represented as points in the plane, and if x and y were subsets of the real line, this would be exact. Otherwise, it's just an illustration. So the first inequality here is just saying that the x projection is less than the hypotenuse. Kind of obvious geometrically. The same for the y component. While x and y are here symmetric, you could switch the order of components. And the other one is essentially a form of triangle inequality, that the distance of the hypotenuse is at most the distance of the x plus the distance of the y. The last one is not sharp. You could prove something better with the Cauchy-Schwarz, but it's fine enough. So, okay. Well, let's just quickly exhibit how these are proven. They're fairly short, or just at least the ideas. Well, if you look at the expression of the distance, so distance p to q, well, this was the square root of the x distance, and I'll skip the points here because those just obscure the notation. And then the distance in the y components. Well, if you want to give a lower bound, what you can do is you can drop a term. This is a positive term, so if you drop it, what you get is square root dx squared. Square root is an increasing function. Well, what is this? This is absolute value of dx, but dx is positive. So this is a and b, essentially. So for b, we argue by symmetry. Okay, so that's the x distance being less than that. Well, the other direction is that you have distance pq. You want to give an upper bound for this in terms of something simpler in the x and the y. And well, again, I will use this abusive notation to skip the what goes into the parameters. So it's the x components and the y components of these points always. So you want to give an upper bound for this. Well, if we square this, then what we get is distance squared is less than or equal to, or is equal to distance x squared plus distance y squared. Okay, we want to complete the square. Why do we want to do that? Because we want to take an easier square root. So what we can do is we can make that less than or equal to, and then add, let's actually put that on a different row, so it's easier to review. So this is equal to dx squared plus dy squared, but this is certainly less than or equal to dx squared, dy squared plus 2 times dx dy. And here the notation is really paying off, because if I put the subscripts there, it would get kind of annoying. So, okay, dx plus dy squared. I just added this positive term here. So most of these estimates, I mean, the trivial estimates that you get are you drop a term or you add a term in order to get a perfect square. So that's one way of getting estimates. There are other fancier ways of using Cauchy-Schwarz and stuff like that. You don't really need them for almost anything in this class, unless you want sharp estimates. But okay, if you take a square root, you get that the distance between P and Q, so square root of the left-hand side, is less than or equal to square root of the right-hand side, which both are now perfect squares. So we get exactly our upper bound. So C is proven. Okay, I didn't set up. You'd have to set up, say, fix x and y, do all that stuff, add a few words to this. But these are the crucial estimates and ideas here to make these believable. So let me just, I'm not seeing the chat right now. So any questions on this argument? So this estimate you can use in R and
outline, right?
Yeah. Sorry.
This is just such a proof outline, right? Not like a formal proof.
That's right. This is just the outline, just the expressing the crucial step of it, essentially. So it doesn't include any of the setup or the conclusion of the statement. So it's just an outline.
Got it.
Yeah. You'd have to add words like fix, P, and Q, and then you'd have to define dx, dy, and then go on from there, things like that. So, but some of these proofs, just because I don't want to be spending time to writing all the details, it's better to focus on the main ideas. You can see the main ideas by many books, like Pugh's book. Okay. So what do you use these estimates for? Well, any kind of statement that involves the metric of the product space. So you can use it for proving things are open or proving that functions are continuous. But a basic statement that I've stated many times, I've stated already, but I left the proof out, so I figured I'd complete that here, just as warm up to these product space ideas. So if you have a sequence of points in the product space, then that sequence converges to another point if and only if each of the components converge. So component-wise convergence is equal to a convergence in the product space. So this, you will remember that this is exactly an estimate that we proved in Rn. And actually, if you think of it, in Rn, we used exactly estimates like this. So this is just a generalization of that. And it might be, you might find it useful to compare these two arguments and see the similarities there. Okay, so this time I wrote a bit more of this setup already in place, so we can just fill in the relevant estimates. So our setup will be, well, we're trying to prove, well, I'm only doing one of these, so I have to decide which direction I do first. So this is doing from the assumption here that if you have a convergence sequence, then you get that the components converge. There is the other direction that will be done later at the end. Okay, so for this implication, we set it up by stating the assumption. So suppose that Pn converges to P, then we want to show that the Xn and Yn converges to X and Y respectively. And I should add here, P is equal to XY is a point in the product space. So that defines us what X and Y are. You could do that before that statement if you wanted to be cleaner. Okay, so then we want to prove convergence of the components. Well, we have to fix an epsilon for that because we have to find an n. And we want to find, and where do we find the n? If we want to be absolutely clear, then we'll first put a subscript here to avoid ambiguities. So there exists a subscript, the np, such that after that index, Pn is very close to xy. Now, okay, we have to make our choices. What is choice of n here? And well, we do it by estimating these quantities. So kind of there's first is our idea. So we estimate, well, the distance between x and x is bounded from above by a lemma of the distance of Pn to xy. And similarly, the distance of the y components is less than distance of Pn to xy. So the projections are shorter. But okay, well, we want, now the question is, can you found an upper bound? Can you make it small by appropriate choices? And the choices are the ones that you make in this step. And the answer is yes. Well, we can make them small if we go far enough. So we can make this less than epsilon and this less than epsilon if we are greater than this index. So now choose n is equal to np. If n is greater than or equal to np, then greater than or equal to n, then we have the statement here. In this inequality, we use star. And so here we are using the choice of np in this second inequality, because this is not always less than p, but it is less than p because n is bigger than n, and n is equal to n. Any questions? So this proves both x and y convergence simultaneously. The same n works. The small one. Okay. Feel free to come back with questions. Now, going the other direction, David, do you have? So going the other way, supposing that the components converge. So suppose we have that xn converges to x, yn converges to y, and let's state what it means. So there, for every epsilon positive, we can find indices, and these can be different indices, and that's why we have to put different subscripts. So n greater than nx, x is very close, n greater than ny, y is very close. You want to use suggestive subscripts to make it clear. Okay, then we have to make a choice. And we do that by, again, going first to our estimate and then figuring out what we need for that estimate. Well, our lemma, and we want to estimate in some easy way by the components. So our lemma tells us that the distance between the pair is the distance of the x components plus the distance in the y components. Okay, well, this is a sum of two things. again, the same question. Can you make the right-hand side small? If you cannot make it small, you have to estimate more. But now you can make them small. Y can, well, X is converging to X, and Y is converging to Y. So we want to make these less than, we have two terms, so we want to make them each less than epsilon over 2, so less than epsilon. So how do we make our choices here then? So for epsilon equal to epsilon, for epsilon equal to 2 in, let's give it this a name, in star, there exists nx and ny so that star holds. We should put the implications here. This way we don't have to repeat the statement. Now, these give us two indices. We need simultaneously for both these estimates to hold, so we take the maximum. So now pick n is equal to maximum of nx and ny, then we show that it works. So if n is bigger than or equal to n, then we go on from here. So this estimate was valid, and we should highlight where we use the choice. So in this case, by choice of n here and star combined. Okay, so very, very basic things. This is mostly review, but questions on this part? Let's scroll through this proof. So we had an if and only if statement with two directions. In one case, we prove that the components converge, assuming that the sequence converge. So we estimate components by the distance above. In the other direction, we work very similarly, but we are in the product space, and we have to estimate that distance from above because we want to make it less than epsilon. Okay, but that then completes the proof. Done. Okay, the same proof works for all other metrics. Actually, the same lemma would give estimates that would work for all other metrics dp that were defined, as also discussed in the book, and also d infinity. What follows from this is that convergence in any of these metrics means the same thing. So convergence, because any time it means component-wise convergence, so they mean the same. Convergence independent of metric, choice of metric. Okay, so that's about sequences, so finishing that proof. Now we want to apply similar things to compositions and to we want to express things as compositions of things to show that they're continuous. So we need a little theorem in the place. You've seen such statements, but I'll state it for a metric space. So suppose f is continuous from x to y, g is continuous from y to z, then the composition of these functions is continuous. So this is at the value x, this would assume the value f of g of x. So one way to visualize these is that you have the space x, f maps that into some subset of space y, and then g maps all those points into space c. And well, this function should be continuous intuitively because if you change x a little, g changes only a little, and then by continuity of f, f changes only a little. But you have to write this carefully when you do up. So we have to take our setup. So let's say f is continuous, g is continuous. We want to prove continuity, so we fix a point x, and we fix an epsilon. And then what we have to do is we have to choose our delta this time. Last time it was choosing our n. And this time the estimate is better to, because there are two different functions, we have to be careful how we choose them. So we want our function value of the composition to be within this epsilon ball. Well, what does that require? That requires that what you plug into G, it has to be in some smaller set. But within this smaller set, there exists some delta ball, some delta G ball, so that any value here will get mapped into this blue ball. Okay, well, F is continuous. So if we use epsilon equal to dg, then that means that, well, there's some blob, that's the pre-image of the purple ball, and within it, there is some radius delta. So this means that, okay, from epsilon, we get a dg, delta g, and then from that, we get delta. And this time we really have to be careful because delta is very different from delta G in general. Okay, so let's proceed by this way. So since G is continuous at G of X, there exists a delta G positive so that if distance of Y to G of X, and you could specify a subscript Y if you wanted, here is less than or equal to delta G, then the distance of f of X. And that should be, yeah, f of X. So then the distance between G of Y and G of f of X is less than epsilon. Okay, well, now we have to ensure that this holds. So since f is continuous at X, then there exists a delta positive so that if distance in the X side between X and Y is less than or equal to delta, maybe we should use it. It doesn't hurt to use the same Y, but let's put a Z there. If the distance between X and Z is less than or equal to delta, then distance between, and let's put a delta F there, just to indicate that this depends on F, and then we make our choice. So distance between f of X and f of Z is less than delta G. So now, if we are this close, our function values are that close. If the function values are that close, then the composition is that close. So let's write out the choice. So we pick delta equals delta F. If now distance in X between X, Z is less than or equal to delta F, then distance between f of X and f of Z is less than delta G. And here we use, let's give these estimates names so we can refer to them. So there's 1 and there's 2. So here we use by 1, and then by 2, since this point is close enough to that point, then we can compose with another function. So distance between G of f of X and G of f of Z is at most epsilon. And this is what we wanted. So distance between G composed with f of X and G composed with f of Z is less than or equal to epsilon. Okay, so compositions are continuous. Any questions? Okay, so now a theorem that really gets into the product spaces. This one I will leave this time unproven. So we proved all the other ones so carefully, but there's an outline here that you can use. So f is continuous from X to Y, G is continuous from X to Z is the setting. Then you can say a few things. First of all, if you place those functions as components of a single function. So H sends X to a pair FG. So X is sent to F and G. And this is a map from capital X to Y cross Z. Then this function is continuous if f and g are continuous. And conversely, if h is continuous, then its components are continuous. Actually, it's a nice exercise to try to prove it using the theorem that we said earlier. There's a setup here that very suggestively says, well, if you know that f is very close and g is very close to its values, then you know that they lie in a small square. Well, you can fit that square in a small ball. But the estimates come from the lemma when you prove them rigorously. Now, B is explicitly in your homework. And C is actually a picture proof, if you are careful. I mean, you need to add words, but to indicate a scheme of this, okay, you have your function h, which sends into y cross z. So x is sent to f of x, g of x. We know that this function is continuous. And part B that is in your homework says that if we take yz here and send it to its first component, so forget about z, then this is also continuous. Now, if we compose these two functions, so pi of y composed with h, what we get is the y component, so the first component in this case, because y is the first factor, which is f. So this composition now, by what we just said, composition of a continuous function and another continuous function is a continuous function. Similarly for g. And this kind of pictures lead to things like category theory. I mean, I won't talk about that, but just if you're passionate about math, you'll find this interesting. So this is a common way that you can prove continuity of things by drawing appropriate diagrams of things. So this expresses it as a composition of two things. I mean, in words, you'd have to add more. Now, our goal is to talk about sums of functions and products. So we need a little lemma. If you have a sum of two real numbers, this is a function from r cross r to r. This is continuous. The product function is continuous. So this sends x, y to x plus y. And then the other function sends x comma y to x times y. Both of these functions are continuous. And then last time we were using a little bit that the inner product, if you take two vectors in Rn, then its outcome will be continuous in those sums. I mean, in fact, it's a sum of functions in this class, so it could be proven by induction if you wanted. You can also use Cauchy-Schwarz if you want. But I'll leave this also for now as an exercise. But, okay, so what can you do with these? Well, if you have two continuous functions, or you have a n by n matrix, then by what we have just said, you can show things like f plus y g is continuous, f times g is continuous, f divided by g is continuous. And if you send a pair of vectors, v, w, to the inner product of av with w, and this was an expression that came up in the lecture last Monday, then this function is continuous. So this is just a statement about continuity. And again, I'll show you the pictures, how to realize these as a composition of things, pieces, that you can express easier. So in the first case, you have a map that sends x to the pair f of x, g of x. And then you have a function. So this is h. And then you have the function plus that takes that pair and maps it to its sum. Now, what happens if you compose these? You first become a pair, then you add the components. So what you get out is the function fg. Well, f and g are continuous, so this is continuous, and this is continuous. So composition is continuous. Each part is continuous, so composition continues. Now, similarly for the other case. So you have your map H defined exactly the same, but this time you use the product map. Composition of these two things is continuous. This way you don't have to prove many things. Okay, what about division? Well, you have to worry about not dividing by 0, so you have to exclude the set 0, but okay, let's express multiplying by division. So first, 1 over g. How can we express that? Well, we first have the map g, and then we have the map x is sent to 1 over x. So this is mapped to r excluding 0. So g is continuous. This map is continuous by 131a, and their composition is 1 over g. Okay, so 1 over g is continuous. So if we combine that, so we take h of x that sends to 1 over g and f, and then we take the product function. Then again, we get that the composition, f over g, is continuous. And where this all gets perhaps the most powerful is when we talk about those Monday lecture things, because there the notation really gets kind of confusing if you try to prove things directly. Is the case C, in which case what we have, well, we have V is sent to, it's actually Rn cross Rn, so we have W, V is sent to, let's write them in the correct order. So VW is sent to AV and W the pair. Now each of the components is continuous. This is a linear map, actually. And then you have the inner product map, which was by lemma continuous. So sometimes this is noted by A comma I because the first component is given by A and the other component is multiplying by. But again, as composition of continuous functions, you're continuous. Any questions? So these are, again, not complete proofs. You'd have to add more words. But the point is that if you have these lemmas, and you can use these lemmas a lot of the time unless you are explicitly told not to, then you can prove continuity pretty quickly by saying that things are compositions of other things. So thus ends our section on product spaces.